So begins the second reboot of my series, RSA to Group Theory, an attempt to explain group theory starting with the RSA algorithm. I wanted to do this series because I've seen many depictions of the RSA algorithm. It's actually rather simple in books with no real good explanation for why the algorithm works. Or how the various parameters involved are selected. They'll give formulas for selecting the parameters that could be followed by any programmer and would work, but they don't give reasons why those formulas work. And so it leads to an algorithm that operates very mysteriously. I also think it leads to an algorithm that it's possible to implement very poorly because you don't understand how it functions. If you choose your messages or your keys poorly, the algorithm can actually break in rather spectacular ways. And if you don't understand how it works, you won't understand why these breakages are happening or know to program around them. Again, if you follow the formulas in books or use a library, then it may have handled these things for you, and so you don't have to worry about them anymore. But again, I always think having a fairly deep understanding of the algorithms that you're using rather than just copying recipes from a book is a much better idea. And in order to understand how RSA and the related Diffie-Hellman algorithm work, it's important to understand group theory because those are the analysis tools that underlie the theory of why these algorithms do what they do. So let's start with the RSA algorithm. Now I have this package that I've written, the Galois field package. I may be mispronouncing that. I am not somebody who's ever taken French. Galois. And this is available on GitHub. It's also available on OSDN. I'm a Mercurial user. I don't like Git at all. And so I actually use OSDN as my primary place to put things because it supports Mercurial natively. But I put things up on GitHub because I recognize that everybody expects things to be put up on GitHub. And it's relatively easy to get Mercurial to talk to GitHub. The GitHub URL for this is something like this. And this package contains a bunch of functions that I use. I made it for playing around, in fact, with an aspect of group theory called Galois fields, which, as a side bonus, are really important for understanding the CRC algorithm and the Reed-Solomon algorithm. In addition, they provide the theoretical underpinning for understanding why elliptic curve cryptography works and why people talk about elliptic curve RSA or elliptic curve Diffie-Hellman. Why there's elliptic curve variants of these algorithms, what that really means. So without further ado, let's get into how does RSA function. So I think most people who know something about RSA, the people who would be interested enough to come to a video with a title like this, would know that RSA, the public key consists of two very large prime numbers multiplied together, and then the private key is what those two prime numbers are. And the difficulty of RSA involves getting from the public key to the private key is very difficult because factoring really large numbers is very hard. All that's well understood. But the question is why does it work? Like the basic algorithm for RSA is something like your encrypted message equals your message to the power of a public exponent percent the public key, right? So M is the message. We'll yes, using E twice in here, public exponent and E. Um, Public exponent is usually shared by everybody using a particular implementation of the RSA algorithm. And E is the encrypted message and M is the message. This is the typical way of using it. It's something like this. And percent is the mod operator. Basically, get the remainder when you divide by this. So if I do this, I'll get a syntax error, of course, because M doesn't exist. By the way, I'm using Python 3.9 here. So, sys.version. And I'm running it inside of the most excellent community edition of PyCharm. Because yes, it's very useful for having a console and being able to switch between the console and the editor, and it's very convenient. And it also understands type annotations and will help you out there. And as such, I'm actually using Python 3.9 type annotations. And so if you want to use these files as is, you will need Python 3.9. They can be easily edited down. You can remove the type annotations. They're totally unnecessary. And if you do, then it will run in any version of Python 3. Okay, so since the RSA algorithm involves these two primes, we're going to pick them. And I'm going to tell you that the primes have to have an interesting property. So we're going to decide that our public exponent here is 5. Okay. And so then that means that our the private keys that we choose, the primes that we choose, have to have the property that p minus 1 percent 5 not equals 0. So basically, that whatever the prime is, if you subtract 1 from it and divide by 5, it doesn't divide evenly. It's not divisible by 5. And again, we'll get a syntax error here. Who cares? So I'm going to choose the primes 23 and 59. So we'll say priv key equals the tuple 23, 59. Okay. Now, if we look, 22% 5 is 2, so that's great. 59% 5 is 4, and so that's great. Now, if we were going to do signing, we would have a different public exponent to use for signing. And there's a good reason to choose a different public exponent for signing. It's essentially so that people can't trick you into signing messages to make it to have you decrypt them. And so you want to have a different public exponent for signing than you do for encryption, because you do not want people to be able to send you messages to sign that mysteriously result in you decrypting something for them. And why that works has to do with the rather symmetric nature of encryption and decryption in RSA. Despite the fact that that's an asymmetric key algorithm, otherwise known as a public key algorithm. So the private keys are 23 and 59. And just in case we decide to do some signing here, we'll decide that our public exponent for signing is 3. And so 22% 5, or percent 3 is 1. Oh, I did 59% 5. I should have done 58% 5. 58% 5 is 3, and 58% 3 is 1. So those primes are good. They will not trip us up. They are not divisible by any of our public exponents. Now, of course, they're very tiny, and in a actual real life situation, you would never use primes that are anywhere near this tiny. You would use a prime that was, something like at least, this size. That's the absolute minimum number. And of course, you'd never use this number because it's a power of 2. It's not prime at all. But this is the number that you would maximum size. And I actually think that it exceeded the width of the display. So let's go here, and indeed, as you can see, that number stretches on for a good long way. let's see if I can get this to print in a, what happens if I print it? Oh, that's not good. We won't bother. Suffice to say, it's a very, very big number. And as I said, the primes that you would typically use actually would be maybe about half this, a square root of this number. Actually, you would use something like, in fact, the minimum size number you'd use for the prime would be actually that. That's the size of the public key. You'd want a public, and then the two primes multiplied together have to be, at least that. So then the two primes each have to be at least that. So you'd use a number like that, which, as you can see, is a very large number. And 23 and 59 are nowhere near that size, so they are completely insecure. I'm using them only for demonstration purposes. So here's our private key here. It is 2359. So let's go and find out what the public key is. So the pub key is priv key 0 times priv key 1. So the pub key is 1357. Okay, that's good. So we tell everybody, the entire world, we tell 1357 is our public key. And in secret, we know that 1357 is really 23 times 59, and nobody else will be able to figure that out. So let's do an encryption here. Let's pick a message. And because our keys are kind of small, we're going to pick a numeric message. Like if you're a programmer, you know how to encode a bunch of text as a number. It's not hard. But we're going to pick a number here just to make everything like nice and pure, so that we aren't worried about some of the other aspects of what we're doing. And the number has to be less than 1357. Let's pick 62 as our number. So then what we do is if we scroll back up here and look at what I said, the algorithm here is m to the public exponent percent public key. So we'll pick 2. And our public exponent we picked was 5. And then percent pub key, which happens to be 1357. We just picked it. Okay. So that's our encrypted message, 420. Well, I didn't choose that on purpose. So 420 happens to be our encrypted message. But how do we get back 62 from 420? It's an interesting question. The other thing is, of course, is it would be really easy to take the fifth power or the fifth root of 420, except 62 times 5 is way bigger than 1357, and so it's actually really hard to take the fifth root, which means that your message to the power of your public exponent has to be less than has to be such that it's much greater than the public key. That's one rule. So that's one of the reasons why some of the weird message padding rules exist for messages in RSA, is because you want to ensure that's the case. It's not too hard to ensure that's the case, but you do want to make sure it is. In fact, what you want here is math.exp math.log. We'll do a poor man's cubed root here. Math.log pub key divided by 3. So that means your message has to be at least 11. It should probably be, at least twice 11 or something. And 62 is, obviously large enough. So we've encrypted 62 and we've gotten 420. So how do we get from 420 back? Well, we're going to import this numtheory utils thing that I have, that I wrote. And in numtheory utils is this thing called multi-inverse. And if we do a help on it, I did actually document these functions. So this does something kind of peculiar. You give it a couple of numbers and it returns you a number that new number that satisfies this formula. You know, you have your a and b. It gives you something that a times n mod b equals 1. And so we're going to get and this will be called secret exp equals mult inverse. Then we're going to pick 5. And then we're going to pick our public key. Except we're not. We're going to pick priv key times priv key 1 minus. So we're going to use the two elements of our private key here to come up with this multiplicative inverse. And then we're going to multiply minus the one key minus 1 times the key component A minus 1 times key component B minus 1. I mean, why on earth minus 1 here? I mean, but you can see how, because we're using components of the private key here to compute this secret exponent, that in fact the secret exponent is kind of would actually reveal in a certain way the components of the private key were you to actually tell people what it was. So the secret exponent is something that has to be kept secret. It has to live only on the computer, probably should only live while you're actually doing a decryption. Because it's essentially learning it is equivalent to somebody learning the private key. And why did that not work? Oh, it's because it's not just mult inverse. I should have done, in fact, I'll do that. From num theory utils, import star. There we go. Now it will work. Okay. So we have our secret exponent here. And we can see over here on the side where it shows other variables. In fact, I should have done m equals 62. And then e equals m star star pub exp percent pub key, like that. So all these variables are sitting over here. 420 is over here, 62 is over here, all that stuff. So our secret exponent is 1021, and just, there we go, 1021. So now let's see, have our secret exponent. Well, we're going to do this. E star star secret exponent percent pub key. We got 62, which is, of course, our original M. So we got our original message back. And, well, that's kind of weird. I mean, secret exponent, we derived it from the private key 0 minus 1 and private key 1 minus 1. I mean, then we're presenting the public key. Like, why does that work? I mean, what's the public key got to do with those other two things? Because the public key is priv key sub 0 just multiplied by priv key sub 1. There's no minus 1 involved at all. So why does the percent work at all? Well, this is interesting, but it works. That's like the standard formulation of the RSA algorithm right there. And signing is just kind of of the reverse. So we'll pick sign exp equals 3. So then what happens is you come up with secret sign equals mult inverse 3 comma priv key sub 0 minus 1. Again, this minus 1 here. Right. And then so So then secret sign is our secret signing exponent. When we pick some message that we want to sign, like we send out everybody the message like 857, right? So then we want to secret sign %pub key. So we send out 857. We tell everybody the signature for this is 1158, and then anybody, because the signing exponent is public. Everybody knows the signing exponent, so anybody in the entire world can do this, and everybody knows your public key, so they can do this, and they can get back 857. And so indeed, you produce this number 1158 that when you take it to the signing exponent power, you get the original message back. And well, so the only person who could have come up with that number 1158 that has that bizarre property would have been you, because you know the private key that the secret signing exponent that you never told anybody was derived from. And so because you know that, you could produce 1158 and nobody else could have. Again, the numbers in actual practice would be much, much larger. But that's how signing works. Signing is basically the reverse of encryption. You decrypt, you apply the RSA decryption algorithm, essentially, to some public message that you told everybody, and then you spit out the results of that decryption, and then everybody tries to encrypt the decrypted message and to see if it comes back to the original. And if it does, that means only the person who knew the secret behind the public key could have created the decrypted signature. And so that's how encryption works. And that's also the reason why you can't use the same exponent for signing as you do for encryption, because somebody could just try to trick you into signing a message that you'd previously encrypted, and then you would have the effect of decrypting it for them. And that's no good, because they're essentially inverse operations. Okay, now let's go on to Diffie-Hellman. There's a couple parameters for Diffie-Hellman. One of the parameters for Diffie-Hellman is another prime, and the Diffie-Hellman prime should have the property. It doesn't have to. It just works nicely. It makes it easier to select a prime if the Diffie-Hellman prime happens to have the property of 2 times p minus 1, or if p minus 1 is also prime. So that. And if you're not familiar, // is integer division in Python. If you divide it by 2, normally you'd get some floating point number like, 1 divided by 2 in Python is 0.5. But when // 2, integer division is 0, because 2 doesn't go into 1 at all. So that's the reason for the //. So that's one property you want. So we're going to pick, I've already kind of done a little bit of work behind the scenes, like 83, right? So 83 is our dh prime equals 83. And so then dh under prime minus 1, well, that of course isn't prime, but if divided by 2, then 41, and 41 is prime. So it satisfies the property that, is prime, dh prime minus 1 divided by 2 is prime. So then there's another parameter that we need, and that parameter is something called the generator, for reasons that will be made clear later. And it's kind of nice to pick a generator with a certain property, but it's not absolutely necessary to pick a generator with this property. You could pick just about any generator, although some generators really do work a little bit better than others. The science behind picking the generator and prime pair in Diffie-Hellman is in fact kind of there's a little bit of a black art to it, and the reason why that's the case will be made clear later. I picked a generator here for no particularly good reason. This is not a carefully chosen generator. In fact, actually, I'm going to test something here. Uh, so one, if this does not yield one, something's, or doesn't yield the DH prime, then this something is wrong here. No, one. It should yield one. If it doesn't yield one, something's wrong. Oh, I haven't set G. Yes, that's right. So we're going to pick a generator of 6. Let's try this. Okay. Now the good. Okay. So 6 is a good generator. Or it doesn't suffer from one obvious problem that a generator could have, which is if this also resulted in 1, it wouldn't be so good. It wouldn't be as good a generator. But we'll get more to why that's the case later. And this is an example of Fermat's little theorem in action. If DH prime weren't prime, this wouldn't be 1. At least most of the time. There's a special group of numbers called Carmichael numbers for which that's true. For any G you pick, that somehow will be 1 regardless of whether DH prime is, even though DH prime happens to be false or not prime. But those numbers are rare, and the smallest one is actually much larger than our DH prime. And so we don't need to worry about Carmichael numbers here. But this is an example of Fermat's little theorem in action. This says that if DH prime is prime, then this has to be true. This will always be true. We'll get into why that's the case later. And then this is kind of a different aspect. This kind of formulation plays into the Rabin-Miller primality test. But that's not what we're doing here. We're not doing a primality test in DH prime. We already know it's prime. But the structure of the way this generator works as it's taken to different exponents means something. And this is testing a detail about that structure. And we would really like this to be a whatever DH prime minus 1 happens to be, which that's what it is. The other thing it could be is 1, and that would not be such a happy result. It wouldn't be terrible again, but still not as happy a result. So let's go on here. So the Diffie-Hellman algorithm is not an algorithm for doing encryption. What the Diffie-Hellman algorithm is an algorithm for is it's an algorithm for 2 people, Alice and Bob, to agree upon a key. So Diffie-Hellman allows, without anybody else knowing what that key is. So it allows them to agree on a key that's unique to them that nobody else will be able to figure out. And the way that this works is pretty darn simple. So Alice picks a secret, and it has to be less than a DH prime. And so Alice's secret will pick a secret of 18. And Bob also has to pick a secret. And Bob will pick a secret of 31. It doesn't matter whether the secret is prime or not. So then Alice and Bob decide that they want to talk to each other. So what Alice does is Alice sends Bob equals G star star a secret percent dh prime. So to Bob is 4. So Bob gets 4. And then to Alice equals so Bob is also going to send something to Alice. They can send these things to each other at the exact same time if they want to. It doesn't really matter. And so to Alice happens to be 76. So to an outside observer seeing 4, it's like really difficult to know what Alice's secret is, even though an outside observer might know that she's sending 4 to Bob. They aren't going to know what a secret is. They're just going to know that she's sending 4. And then, you know, somebody who's also looking in on things will see that Bob is sending 76 to Alice, but they won't really know what B secret is, even though they know the number 76. Now again, with such a small prime as 83, it's rather trivial to figure it out. But if the prime is really, really big, it starts being very hard to figure it out. So then on Bob's side, what he does, Bob's secret, or not, it's not the right word. Bob Alice equals to Bob G star star to Bob percent DH prime. So Bob Alice secret. So the secret from Bob's perspective is 51. So Alice Bob secret equals, so Alice got this number. Notice, oh, okay. Oh, what did I do wrong here? I did something wrong. Oh, that's right. That's right. That's what I did wrong. I'm sorry, I got the algorithm all wrong. Please forget that last little bit. I'll leave it in the video because, you know, people make mistakes, and it's, I think, good to show that people make mistakes. But this is a mistake, and I will show you what I should have done here. And it's actually obvious once I thought about it. Like, Bob's secret isn't involved at all here. Okay, so that's what. So now the Bob Alice secret is 9. Okay, so now the Alice Bob secret should have been she should have done this with her secret number. Yeah. So now the Alice Bob secret is also 9. Now, this one is a little easier to see why it works. Like, you're doing G star star A secret star star B secret percent DH prime on one side, which will give us, oh, I forgot this is going to take forever. Here's what we're going to do here. Oh, I might have to actually stop recording for a bit while I figure out how to get this to stop. So we're back. I figured out how to stop it. Yeah, I actually fault PyCharm for not passing in Control C the way it ought to. I might have actually been able to hit like stop console and have it that work. I instead did some Unixy things and made it happen instead. I know what Control C actually does behind the scenes. So the reason why this failed is, you know, that's a pretty large number. And then, right, B secret over here you can all see all of these things over here too, right? Is 31. So this to the power of 31 is a pretty huge number. Um, and actually, I think what was even happening here is, in fact, the binding for star star is the left to right to left. And so I think what we're doing is taking G to this number, and that number is just going to be too huge for words. Like, it's going to be too huge for memory. It just won't fit. And so we are going to force the binding to work the way we want it to work. So one side is doing this. That will be tractable. There we go. And then the other side is doing this. And we can see, that these are like, well, you'd think that this would actually kind of work, right? That this would end up with the same result as that. The real mystery here is, why are 2 Alice and 2 Bob, why is it so hard to get back from 76 and 4 back to the original, for 2 Alice, you get back to 31, which is B's secret, and for 2 Bob, you get back to 18, which is Alice's secret. Like, why is it hard to get back from 4 to 18? Why is it hard to get back from 76 to 31? That's the real mystery. The reason why this works, this intuitively feels like it ought to work. But the reason why the whole thing works, like why you can do percent, why, because we're not actually doing that, right? We're doing this. Right? Why does this and this, this and this, why do they come up with the same result? Why can you just sprinkle in the percent DH prime right in the middle here and expect that you'll get the same answer out? That's another part of the mystery. So let's go on. I think this is a good place for the part 1 to stop, and we'll go on to part 2 next, where we start getting into the details of why these things work.